it to the cloud. All right, guys, good to see you. Good to have you back. So we're going to begin a series of lectures on Bayesian estimation, which is the idea of maximizing the posterior, finding a parameter x that maximizes what are called posterior probabilities. And I want to start with describing how is the Kalman filter that we just learned about, how is that related to Bayesian estimation? And I want to show you that the Kalman filter, which is basically an analytic description of finding a parameter that maximizes minimizes the uncertainty. Remember that we found the trace of our uncertainty matrix, and we found the gain that would make that basically that trace as small as possible. So we tried to learn from our mistake in such a way that would maximize our certainty about what we know. And so what I want to show you today is that how is that related to Bayesian estimation? So first we're going to talk a little bit about Bayesian estimation, and then we're going to see that the two are indeed the same. So basically our story for today is how to do Bayesian estimation, which means finding a conditional probability. So you have an x variable that you want to estimate, and that x variable depends on your y that you just observed. So you want to know what's the probability of x given y. You made an observation y. You want to know what's the probability of x given y, and find the x that maximizes that posterior probability. So I'm going to show you that that's the same as what we did with the Kalman filter. And to do that, what we need to do is a little bit of a kind of a graduate school level matrix algebra. What we have to do is factorize determinants, because normal distributions have a determinants in it, right? You have a determinant of the variance in the normal distribution. And we have to also factorize inverses. So in a normal distribution, you take the variance of something and then you put it in the coefficients of the exponential and you say, I want to invert that. That's how you get this Gaussian distribution. So we're going to have to do a little bit of math to factorize and determinant, factorize an inverse in terms of the things that matter to us, which is the conditional probability. And so once we do that, well, the end of our story is kind of an anticlimax, because at the end of it, you'll see that what the Kalman filter was doing, the equations that we derived, are the Bayesian estimates. But let's walk through it so you can see the story. So in maximum likelihood, what we did is we said, let's find the x that maximize the probability of our data given x. So here's our data that we observed. Here's our unknown. And what maximum likelihood did was to say, given that you have, you want to find this parameter x, find the x that maximizes the likelihood of observing the data given that unknown. And so, we found the maximum likelihood by basically building a statistical model that related our unknowns to our observation, like the 2 GPS problem, for example. So in the Kalman filter, what we did is we said, well, we're going to have a posterior. We're going to call x of n given n, and we're going to say it depends on our prior plus some coefficient k that we're going to multiply, which is the difference between what we observed and what we predicted. So what we predicted. And this was called the Kalman gain. And in order for us to do the Kalman filter, what we had to have is that we had to have a prior, which we said our prior was basically a distribution that looked like this. P of x was normally distributed with some mean that we called x of n given n minus 1 and some variance, P of n given n minus 1. Is the internet turned off?
Yeah.
Okay. All right. Hopefully it won't give us too much trouble. So our prior was something that had this mean, x of n given n minus 1, and had this variance. And after we made our observation, y of n, we had something we called a posterior, which was something that had a normal distribution that had a mean x of n given n and a variance p of n given n. And now what I want to know is that, is this thing that we called our posterior, and we got this, of course, from the Kalman filter equation. So is this thing that we called our posterior, is that the x, I'm going to call it map, maximum a posteriori, is this this quantity? Oops, sorry. Is this quantity? Is this thing that we called posterior, is this the x that maximizes the probability of x given y? If it were, then that's called a maximum a posteriori estimate. So look at the difference between maximum likelihood and maximum a posteriori estimate. In maximum likelihood, what it says is that write a model that says how your data is related to your unknown and maximize the likelihood of observing your data. This is called the likelihood. In maximum a posteriori, it says, given that you've observed your data, what's the most likely unknown parameter x that could have generated it? And of course, when you think about it, map is what you want. Yeah, you want to find what's the most likely x that could have given me, from this data. I measured this data. What's the best x that I have? That's map is what you want. But we haven't done that. We did the maximum likelihood. And then we had this thing in between, the Kalman filter, that gave us something that we called a posterior. But we just called it a posterior. Is it really like the Bayesian posterior, or is it just some name that we picked that happened to be the same as Bayes? And what I want to show you is that it actually is the Bayesian posterior. That's what we're going to do today. All right. So you know that when you take a joint probability between p of x and y, you have the conditional probability times p of y. And that's the same thing as writing it this way. And so we get Bayes' rule. P of x given y is p of y given x, the likelihood, times p of x, the prior, divided by something that normalizes, called the marginal, p of y. Basically, it makes sure that this probability is has an integral of 1 by dividing it by something. So, we had a prior. We called p of x. It was some normally distributed with some mean x of n minus 1 and some uncertainty p of n minus 1. That was our prior. And so if that's our prior, we make an observation y, and that's equal to cx plus epsilon y, where epsilon y is normally distributed with variance 0, with variance r. And so, the expected value of y is c times x of n minus 1. That's our prior. That's what we think we should be getting when we make our estimate y. This is our prediction. And then the variance of y is c times my prior uncertainty, c transpose plus r. So p of y, the marginal for our example here, is going to be a normally distributed random variable with the mean c of x of n minus 1 and variance c p of n minus 1 c transpose plus r. Okay, so what I want to do today is as following. I want to write P of x and y, the joint probability of x and y. So I have some x, and I want to write, given that y is related to x like this, I want to write the joint probability of x and y. And then I want to show you that if I could factor that probability, that joint probability, so that I get a P of x given y and a P of y out of it, then P of x given y, this thing here, is going to have a mean that's going to be the posterior mean for the Kalman filter, and is going to have a variance that's going to be the posterior variance for the Kalman filter. So what I want to do is first write for you P of x and y, the joint probability. So let's see what that is. So P of x and y. So what does this mean? That means you have a basically probability of a vector made up of x and y, and x could be a vector, y could be a vector, but that would be basically that vector put together. That's what a joint probability means. So that's a normal with something that has a mean, expected value of x, and expected value of y, and it has a variance that's a matrix, variance of x, covariance of x and y, covariance of y and x, and variance of y. So when I say joint probability of x and y, I'm talking about probability of some combination of x and y written as a vector, which is going to have a normal distribution of something that's a mean of x, something that's mean of y, and a variance covariance between those random variables. So I want to write down for you what that looks like, the normal distribution of x and y, and then factor it in terms of a conditional probability between them. So to write this normal distribution, I can tell you what variance of x is. Well, so let's write it down. So what's variance of x? That's just my prior variance, P of n minus 1. What's variance of y? That's this equation here. And what's expected value of x? Expected value of x is x of n given n minus 1. What's expected value of y? That's c of x n minus 1, right? I can write you this. I just don't know this one here. What's covariance of y and x? So let's write that down. Covariance of y and x. So what am I doing? I want to write the joint probability of x and y, where x is my prior. It has a mean, x of n minus 1. It has a variance, p of n minus 1. What's y? Y is equal to cx plus epsilon. What's its mean? C of x n minus 1. What's its variance? Variance of y. Now, the joint probability of x and y, p of x and y, also requires me to know the covariances between x and y. So let's derive the covariances. So covariance of y and x, what does that mean? Covariance of y and x is going to be the expected value of y minus the mean of y times x minus the mean of x transpose close the expected value. So let's work this out. So that's the expected value of what's y? Y is cx plus epsilon y minus what's expected value of y? That's c times expected value of x. And then here we have x minus expected value of x transpose. All right, so I'm going to have to multiply some variables here. I'm going to get cx x transpose minus cx expected value of x transpose plus epsilon y times x minus epsilon y times expected value of x transpose minus c expected value of x transpose plus c expected value of x transpose the whole thing. So I want to find the expected value of this guy. Well, this goes away. So does this. So here's what I'm going to get. C times expected value of x transpose, minus C expected value of x transpose, minus C expected value of x transpose, plus C expected value of x transpose. So this, and this are the same thing. So I get C expected value of x transpose, minus C expected value of x transpose. So this is just C times variance of x. So covariance of y and x then is just C times variance of x, which is C times P of n minus 1. That's covariance of y and x. Okay, so now I can write the joint probability between x and y. It's a normally distributed random variable with mean of x of n minus 1. Mean of y, C x n minus 1. That's the mean of this xy joint random variable. Its variance is variance of x. Variance of x is P of n minus 1. Covariance of x and y. Covariance of x and y is just the transpose of this, which is P of n minus 1, C transpose. Covariance of y of x, C times P of n minus 1. And then variance of y. Variance of y is C P n minus 1, C transpose plus R. Joint probability between x and y. When x has a prior, x is our prior, has a mean of x of n minus 1, it has a variance of P of n minus 1. Y is our observation. Its mean is this, its variance is this, and I just computed the covariances between the two. So this is the joint probability of x and y. So what does this mean? This means that this is a normal distribution with a mean of mu x, mu y, and variance sigma xx, sigma xy, sigma yx, sigma yy. Just a shorthand way of writing our equation so far. So the joint probability of x and y is something that has a mean mu x, mu y. It has a covariance of sigma xx, sigma xy, sigma yx, sigma y. We'll hear what those values are. Yeah.
Did you say the covariance of x given y is the transpose of the covariance? So what happened to the transpose over
P?
Yeah.
P is a symmetric, yeah. Okay, all we've done is write the joint probability between x and y when x is our prior. That's all we've done so far. Okay, so why am I doing all this? Well, because what I want to do is I want to show you how to factor this into two things. A normal, which is going to be P of x given y, and another normal, which is going to be P of y. Right? So that's the definition of a joint probability. Joint probability of x and y is by definition the conditional probability times the probability of the second variable, right? So I want to show you how do you take a joint probability, which I just showed you what the elements are, right? So we can write the Gaussian that does this. How do we factor it so that I get this out of it and I get this out of it? Because if I can get this out of it, right, if I can get the conditional probability, then I have the formula for maximizing the a posterior. Because this is what I'm after. So what is this joint probability? So P of xy is this normal. So what does it mean when I write this as a put an n there? What is that referring to? Well, I have an equation that goes like this. You have 2 pi where you have x is size p by 1, y is size q by 1. So it's p plus q divided by 2 times the determinant of the whole thing, the square root of that. So this is this guy here, times an exponential of -1/2 times x and y minus mu x, mu y transpose the variance inverted So that's just a normal, I just wrote a normal distribution for you. I didn't do anything special. In my normal distribution, I just happen to have a vector, xy. Here's what the vector looks like. It has a mean, mu x, mu y. So I take the difference between my variable xy and that, transpose times the inverse of the variance, and this is just going to give me a number, exponential, normalized by the size of that system, which is 2 pi to p plus q divided by 2 times the determinant of my variance raised to the power 1/2. Do you have any questions about that, what I did so far? Do you see? So all I've done is just written a normal distribution. That's all I've done. But the point is, we want to factor this. We want to factor this guy in terms of a conditional and this marginal, P of y. So I want to be able to tell you, how do I go from this, which has a determinant of this system here, raised to the power 1/2, and inverse of this variance covariance matrix, and write it in terms of multiplication of two normal distribution. So for me to do this, right, what I have to do is to take a determinant and factor out of it another determinant. Take an inverse and factor out of it another inverse. That way I can write it as multiplication of two normal distributions, right? If I can do that, then one of them is going to be P of y, the other one is going to be P of x given y. That's the idea. Okay, so if I could do that, then this is equal to P of x given y times P of y, which is equal to, well, what's P of x given y? I don't know. I have to find this. What's P of y? Well, P of y, we know, has a mean that's expected value of y. What's expected value of y? What's variance of y? Right, so this is times 1 over 2 pi q over 2, because I'm assuming that y is a q by 1, times the determinant of its uncertainty, variance, sigma yy, this guy here, which is this term here, that's sigma yy, raised to the 1/2, times exponential of y minus mu y transpose sigma yy inverse y minus mu y closed. So what I need to do is to take this equation, P of x and y, the joint probability, where we have this matrix and this matrix here, and factor out of it this thing here, P of y. If I can do that, I'm going to get the conditional probability. Yeah, do you see it? That's what we're going to do today. We're going to take a joint probability, factor out of the marginal, and get the conditional probability. And after we do that, we'll see that that conditional probability has a mean that's the same as what we call the posterior with the Kalman filter. It has a variance that's what we called the posterior variance with the Kalman filter. That's our idea. Okay, I don't know what's going on.
So maximum minus the one.
Okay. All right. We can move forward. Okay. So, here's our problem. We have a matrix here. Sorry, we have a matrix here, sigma, that we called, had sigma xx, the joint probability, sigma xy, sigma yx, and sigma yy. This was our variance covariance matrix. And what I need to do is to factor the determinant and the inverse of this matrix, right? Because I have to get this inverse to be made up. I can somehow get the sigma yy out of here, out of the inverse. And so to do that, I'm going to have to do some work on the determinant and some work on the inverse. So let me show you how we're going to do that. So suppose we have a matrix M, which we define as some matrices E, F, G, and H. So we're going to define a matrix M made up of E, F, G, and H matrices, submatrices inside of them. And what I want to do is to figure out how we can get this matrix, its determinant, to have something that has determinant of H in it. So I want to factor out of the determinant of M, the determinant of H. And the first step is to diagonalize. What does that mean? Diagonalize M. I want to somehow get M to have something here. Let's call it something phi. Let's call this here theta, and then this 0. So that's what it means to diagonalize M. Somehow do something to M so that I get something in the diagonal elements but nothing in the off-diagonal elements. And here's how you do it. So what you're going to do is to multiply M by something on the left side and then something on the right side. And the important properties of this thing that you're going to multiply is that its determinant is going to be equal to 1. So we're going to take the matrix M and we're going to multiply it by something on the left and something on the right, where the something on the left and right have the determinants that are 1. So here's how we do it. Multiply on the left side by this, and multiply on the right side by this. So let's see if this gives us this is called a sure diagonalization. So look at the left side. Its determinant is an identity matrix times an identity matrix minus 0. Right? 0 times this is 0. Identity times identity is identity. Determinant of this is 1. Determinant of this is also 1. So now let's multiply this by M in the middle. Let's see what we get. So first we're going to multiply this by M. So identity times E minus FH inverse times G. So that's E minus FH inverse times G. Identity times F minus FH inverse times H. That's 0. Similarly, the other two terms. So all I did is I multiplied this by M. Now what I have left is this term here. It's identity 0 minus h minus 1g identity. So now I multiplied once more. So multiply this term times identity times 0 times this term. I get e minus fh minus 1g 0 0 h. All right, so I diagonalized M. Look at this. I've taken the matrix M and I've diagonalized it. Now, you want to ask yourself, why is he doing this? Why is he diagonalizing this matrix? Because look what we're after. We're after this guy here, sigma yy. So sigma yy is h in this matrix here. Look what I did. When I diagonalized it, first I got rid of all these terms other than the diagonal, but I also get h by himself here. Because what I want to do is I want to factor h out of here. And to do that, I have to get it alone and have nothing else in this matrix other than diagonal elements. So I was able to do that. Why do I want to get h by itself? Because I want sigma yy. Why do I want sigma yy? Because that's p of y, right? P of y, I want to factor out of here. P of y has variance sigma yy. So I want to get sigma yy out of sigma. So that's what my first step has been so far, to take a matrix, diagonalize it, and I get h by itself. Okay, so what's the determinant now? What's the determinant of my system? Well, the determinant of this guy, let's call this matrix X, let's call this matrix Z. So the determinant of X, M, Z, the determinant of three matrices multiplied by each other is determinant of the first one, second one, third one. Determinant of the first one and the third one are 1, so that's just determinant of M, which is equal to the determinant of this first term, E minus FH minus 1, G times the determinant of H. This is pretty cool. Look what I did. I found the determinant of the matrix sigma. I have been able to write it as the determinant of E, which is sigma xx minus sigma xy, sigma yy inverse sigma yx times the determinant of sigma yy. I factored out the determinant of y out of the determinant of the joint probability. Look what I got. What was sigma? Sigma was the variance, covariance of the joint probability, x and y, right? I've just showed you how you can take the determinant of this. Why do I need the determinant of that? Why do I need determinant of the variance covariance matrix? Why do I care about determinant? Because that's the normal distribution, right? Because that's in the denominator of the normalization of the normal distribution. So for me to factor out P of y, I have to be able to factor the determinant of the variance covariance matrix. I just did it. The determinant of the variance covariance matrix is the determinant of these elements times the determinants of the variance of y. That's pretty cool. For that, we take a smile and say, that's wonderful. Makes you feel good. Okay, so the first step was the determinant of the variance covariance matrix. The second problem is that inverse, right? So if you go back now, look at my normal distribution. My joint probability has the determinant, which I just factored. So I can now take, I can say what this is. I can take this out of here. But look at this guy here. It has an inverse in it. It has that whole matrix is inverted. And I have to now take out the inverse of the variance of y out of the inverse of the variance covariance of the joint probability. So that's my next problem. How am I going to do that? So, okay. So we have this guy. We have x times m times z. That's equal to something. Here it is. Let's call this W. This matrix W. So look, when I multiply x times m times z, I get this diagonal matrix. I'm going to call that W. Well, what's the inverse? The inverse of this guy? Well, that's x mz inverse is equal to W minus 1. So then z minus 1, m minus 1, x minus 1 is equal to W minus 1, which means that m minus 1 is equal to z W minus 1 times x. Okay. This is very useful. Why? Because it says the inverse of my variance-covariance matrix can be written in terms of my diagonalized matrix times these other two matrices, z and x. So let's write it out to see what it looks like. So what's m minus 1? So here's m. Here's m here. What's m minus 1? Well, that's equal to z times W inverse times x. Here was z. Here was z. So that's I, 0, minus h minus 1g I. That's z. I need to find W of inverse. So here's W. Its inverse is E minus f h minus 1 g inverse 0, 0, h minus 1. That's W inverse. What's x? Here's x. Okay, that's m minus 1. So I have the inverse of my variance-covariance matrix. And we'll have to see if that's going to help us or not. So, let's write down where we are. So we have M, which is this variance-covariance matrix, EXX, EXY. Sorry, the variance of x, covariance of xy, covariance of yx, variance of y. That was our variance covariance matrix. And we determined that the determinant of this is equal to what I wrote up here. The determinant of sigma xx minus sigma xy, sigma yy inverse, sigma yx times the determinant of y. Variance. Okay, so this term here, for our simplicity, since we're going to be using a lot, let me call this matrix S. And now I can write the terms that are going to appear on the left-hand side of our normal distribution. So we're going to have 2 pi minus p plus q divided by 2 times the determinant of this variance-covariance matrix E. Raised to the power of 1/2. So that's the left side of my normal distribution. So I can now factor this out. I can now write this as the following. 2 pi to minus p over 2 times the determinant of s raised to the power of 1/2 times 2 pi to minus q over 2 times the determinant of sigma yy. What I did is that I factored the joint probability distribution, the normalization of the joint probability distribution, which is this. I factored it in terms of this term and this term. So this is related to P of x given y. It's not the whole thing. This is related to P of y, right? So I factored out P of y here. That some of course is not. I still don't have the exponential, but I have the normalization of that exponential term. So I have now something that depends only on y, and I have the remainder, which must be that part of P of x given y. And here it is. Here it has this determinant in it. It has a variance of xx and covariances, variance of y, and covariance of y of x. So that's my first step. I've taken the left part of the equation, this guy here. So I've taken this part here of the joint probability. I took this part and I showed you this. I can split it into two parts, this part and this part. Okay. All right, now comes the inverse that I have to split. So the inverse has this part in it. So the rest of my normal distribution has this exponential that has a minus 1/2 times x minus its mean, y minus its mean, times this matrix inverted. Right, so that's what's remaining in my joint probability distribution. So this is the thing that I have to factor. How am I going to get something that just has sigma y out of here? So what I showed you is that M inverse has this shape. So that means that this variance covariance, its inverse, I can write it using this equation. So that inverse is equal to identity. So I'm just gonna copy these guys and replace E, F, G, and H with this. Instead of E, I'm gonna have sigma xx. In terms of F, I'm gonna have this. Instead of G, I'm gonna have this. And instead of H, I'm gonna have this. And I'm just gonna rewrite this equation so that I get the inverse of the variance covariance matrix. And here's what I'm gonna get. Now this term, finally the last term. So that's the inverse of my variance covariance matrix, where S here is this quantity. Okay, so next step is I'm going to have to multiply this vector transpose times this inverse times that vector. So I'm going to get a scalar. But in order to do that, I'm just going to have to do a little bit of algebra to work through it. So all I'm going to do is I'm going to multiply this vector transpose times this inverse times this vector. Let's work through it. So I'm going to get x minus its mean transpose. So I'm just going to multiply this by this element now. Minus y minus its mean transpose times sigma yy inverse sigma yx, comma, so this vector times this row y minus mu y transpose. So this vector transpose times this matrix. Here it is, this first part of this matrix. That's all I've done so far. Right? So this times this times this times 0, this times identity. All right. The rest of this is s minus 1, 0, 0, sigma y minus 1, and I minus sigma xy, sigma yy minus 1, 0, and I. Times the vector x minus mu x, y minus its mean. So we're going to multiply it through. And when we do, here's what we're going to get. I'm going to get x minus mu x plus sigma xy, sigma yy minus 1, y minus its mean transpose s minus 1 times x minus mu x plus sigma xy, sigma yy minus 1, y minus mu y plus y minus mu y transpose sigma yy inverse y minus mu y. All right, let me pause for a second and see what we just did. We took the exponential of the normal distribution, which had the variable x and y. So you take the mean of x and y, you subtract it out, you transpose it, multiply it by the variance-covariance matrix, multiplied by itself. That's the normal distribution, the part that has the exponential in it. We took this inverse, we split it into 3 terms, and then we multiplied this through, and after we multiplied it through, we gathered all the terms that had dependence on x, and I wrote it down here. So here's matrix, here's vector x minus something times s minus 1 plus this term here. So this should be familiar to you. This has things in it that's p of y, right? It's y minus its mean times the inverse of the variance of y times y minus its mean. So this is the part that has p of y in it. All the rest that's left must be p of x given y. So now I can write p of the joint probability distribution is 2 pi minus p plus q divided by 2 times the determinant of the variance-covariance, square root of that, times the exponential, minus 1/2, x minus its mean, y minus its mean, transpose, times variance-covariance, inverted, x minus its mean, y minus its mean. Okay, so this is our joint probability distribution. What I did for you is to factor out this into this following. The determinant, we factored it to be minus p over 2 times this matrix S to the minus 1/2 times 2 pi minus q over 2 times the determinant of sigma yy to the minus 1/2. And then what I did is that I factored the exponential. So this is times the exponential of minus 1/2 x minus mu x plus, here it is, up here, sigma xy, sigma yy minus 1, y minus mu y, transpose s minus 1, x minus mu x plus sigma xy, sigma yy minus 1, y minus mu y. That's the first exponential times the exponential of y minus mu y transpose sigma yy minus 1, y minus mu y. So I've factored the joint probability into this term, the first term here. This is P of x given y. This is P of y. Let's write it down. Okay, so this is equal to P of x given y times P of y. So I'm in position now to write for you our story, the end of our story. So we started with the following. We started with a prior. We said P of x was normally distributed with mu x and sigma xx. And we said that's equal to a normal distribution with our prior, x of n minus 1 and P of n minus 1. We have an observation, P of y, where that was also normally distributed with mu y and sigma yy. And that was a normal with mean c x of n minus 1. Variance C P of n minus 1 C transpose plus R. So what does that mean? That means that my P of y was equal to 2 pi minus q over 2 variance sigma yy is determinant to minus 1/2 times the exponent of minus 1/2 of y minus mu y transpose times sigma yy minus 1 y minus the mean. So now from this I can tell you what's P of x given y. P of x given y is what's remaining. So P of x given y is this part here, this term up here. Let's write it out. That's 2 pi minus P over 2 times S, the determinant of S. S was sigma xx minus sigma xy, sigma yy minus 1, sigma yx. The determinant of this, find the square root of it, multiply it by the exponential. times s minus 1, which was sigma xx So what I have is that we have this prior which has a normal with mean x of n, n minus 1, and uncertainty p of n, n minus 1. And the covariance matrix sigma xy was p of n, n minus 1 c transpose. We did this a little while, just a few minutes ago. The covariance yx was c p of n, n minus 1. The variance of y was c p of n, n minus 1 c transpose plus r. So let's write down what is this joint distribution. Now that I have all these variances here and I have all the means, so what exactly is this joint distribution? Sorry, this conditional distribution that I've been talking about. So my conditional distribution is p of x given y is a normal with some mean expected value of x given y and some variance of x given y, right? So this is, here it is. Here's the conditional probability here. So its mean is this. Its mean, the expected value of x given y, is this quantity, x minus mean of x plus sigma xy, sigma yy minus 1, sigma yx, right? So that's, sorry, I miswrote. So it's this term, x minus mu x plus sigma xy, sigma yy inverse times y minus mu y. That's the mean of this. What does this mean? That's x, the expected value of x given y, sorry, it's just this term here. There's no x here, right? Because this is x minus the mean. This is the mean here. So mu of x is x of n, n minus 1. Sigma xy, what is that? That is p of n, n minus 1, c transpose. Sigma yy, it is this quantity here. C, p of n, n minus 1, c transpose plus r, quantity inverse, times y minus, what's mu y? That's c x of n, n minus 1. Okay, look at this. This is saying the expected value of x given y is your prior plus something that's multiplying what you observed minus what you predicted. What is this? That's the common gain. Say hallelujah. That's a beautiful thing. So what was common gain? The common gain was the ratio of your prior uncertainty to your measurement noise, right? So here's the variance of your observation, and here's the prior. So that's in fact these two terms. It's the multiplication of the covariance times the variance, the inverse of the variance. All right, that's the expected value. What's the variance of the conditional distribution? It's this term here, inverse. And let's write the variance. It's sigma xx minus sigma xy sigma yy inverse sigma yx. That's the variance of x given y, right? Because that's what we're inverting here in our exponential. We're inverting the variance. Here it is, the variance here, determinant of it, raised to the power 1/2. So what is this? Sigma xx, sigma xy. So that variance is equal to the variance of x, the uncertainty, p of n given n minus 1. Refuses to erase. That's the first term. Minus the covariance of x and y. That's this term here. Times sigma yy minus 1. That was just a common gain. Times what's left, sigma yx, which is the covariance between y and x, which is c p of n minus 1. That's equal to identity minus k of n times c p of n minus 1. So the posterior mean is what we've been calling x of n given n, right? Oh my God. Oh, that's terrible. Sorry about that. So the posterior mean, look at it. It is the mean of this posterior, which is basically you take your prior, you multiply the Kalman filter times the prediction error. That gives you the posterior mean. The posterior variance, x of n, p of n given n, here it is. This term here. So I don't know. Okay. All right. All I want to say, all I want to tell you guys, I don't need to write this anymore. All I want to tell you guys is that what we tried to do is to take the joint probability, which is the taking a vector, x and y, finding its variance and covariance, and factor out the y probability. And by doing so, we end up with what's left, which is the conditional probability. And what I showed you is that that conditional probability has a mean, that's the posterior that we called before. It has a variance, that's the posterior that we called before. And so the Kalman filter is estimating the map, maximum a posteriori estimate. It's finding the mean and the variance of the posterior distribution, which is the conditional distribution that we were going after. All right, any questions? Okay, see you Tuesday.